So in the handouts that you've got, we've got one more topic to cover, data link control protocols. And then I'll provide some new handouts hopefully next week for the rest of the topics. So far we've looked at how to get data across a single link, looking at how the signals are formed, the different ways to encode data onto signals, the different signal encoding techniques, and we looked a little bit about error detection and correction in the last topic before the midterm. You've had your midterm. We've got one topic here which is still about the data link layer. We've focused on the physical layer and the data link layer aspects. And then after this topic, we'll move up to the network layer. How does the internet work? And how do internet applications work? Will be the remaining topics of this course. But here we need to talk about a couple of more parts about how the data link layer works. We're going to look at all the general components of data link layer protocols, but we're going to focus on two parts, flow control and error control. So the physical layer, in the simplest terms, we think it tells us how do we transmit signals across a link when we have data to send. We've got data to transmit between one computer and another. The physical layer is how do we create the signals to be transmitted. But to communicate across a single link, we need more than just sending signals. We need some what's called control and management of how we send the data. Some examples of the tasks needed to communicate across the link: synchronization of a frame. What's a frame? A frame is a block of data, a block of bits. We send one block at a time, say a frame of bits. The receiver needs to know when does the frame start and when does it end, to synchronize at least the starting point of that frame. Data link layer or data link control protocols, some of them include features for synchronizing the start of the frame. Ethernet and wireless LAN, which includes data link control protocols, include frame synchronization. Flow control, which is making sure that the sender does not send too fast for the receiver. If I talk too fast, then you may not be able to take in everything that I'm saying. Same with our computers. If one computer sends too fast for the receiver will overflow. We'll talk about that in more detail today. Error control, we've spoke a little bit about that already. We transmit our bits. What happens if the receiver detects a problem, detects errors? We need some way to fix those errors. So error control is part of the data link layer control protocols. Giving endpoints or stations addresses, what format of addresses to use, is commonly a part of data link control protocols. And other aspects of managing the link, setting up the link, that is making sure that before I can transmit my signals, that the receiver is ready to receive those signals. It's in the right state, it's turned on, for example. So managing a link. So there are a number of features which are important for data link control protocols. They're part of the data link layer. So we sometimes refer to either data link control protocols or simply data link protocols. In this topic, we're going to focus just on two features, flow control and error control, perhaps the two most important features. For those people who just came in a little bit later, then we'll go through the exam. Well, I'll give you your exam to look at tomorrow in the lecture. Let's make sure the air conditioner is on, please. Both there and the back one. So everyone is fresh for the last lecture of the day. First, we'll focus on flow control. What is it and how does it work? We're still considering transmitting between one computer and another computer across a single link. So the source computer has a sequence of bits to send. It transmits some signal that represents those bits. That signal goes across the link, and the signal and therefore the bits are received by the destination computer. This is some picture of what happens at the source and the destination. This is the source computer, this is the link between them, and the destination computer. If we focus on the data link layer, at the physical layer it takes bits and creates some signal to send. We don't care what type of signal at this stage, we just know that we're going to have bits and generate some signal depending on what medium we have. What normally happens is that there's a higher layer, the network layer. We receive data to send. That is, someone at the computer has pressed send. The send button generated data to send to another computer. It comes down to from the network layer, that data to be sent, let's say a sequence of 100 bits, is delivered to the data link layer, and it's stored in some memory allocated for the data link layer. So some memory on board the computer or on board the network card. That memory, or sometimes referred to as a buffer, it stores those bits before they are transmitted. So basically we have some data, it's put into memory, and the data link layer takes that data out of the memory, does any processing it needs to do, and transmits it as a signal or a sequence of signals across the link. So this is memory inside the data link layer. It may be implemented in your computer or in a network card attached to your computer. Memory has a fixed size or a limited size. We don't have an infinite amount of memory. We have a fixed amount, a finite amount of memory. So we must deal with what happens if the memory becomes full. Let's look what happens, especially from the receiver's perspective. We receive data, put it inside the memory. When the transmitter's ready, it would process the frame, the sequence of bits, and transmit. And when the signal's received, it will be put inside memory at the receiver device. And when the receiver is ready to process that, it will remove it from the memory and send it to the network layer. So each frame has some size, some, let's say, X bits in length, X bits of data. That is, we receive X bits of data from the network layer, it's put inside memory, process and send. Of course, we may receive more. That is, a lot of data may need to be sent, and therefore we receive data over time and put it inside memory, transmit. And as we receive, we put it inside memory or a buffer at the receiver. And only when the receiver is ready to deliver that data to the higher layer will it be removed from that memory. So, if we have a fixed amount of memory here at the receiver, if we say the memory allocated for this data link layer is, let's give X a number, 100 bits each frame, we allocate 300 bits as a simple example. That is, our buffer size is 300 bits. Then what happens if we transmit data as a single frame? That frame is received, put inside memory. We had 300 bits of memory. We've currently got, it's storing the first frame. That is, it's storing 100 bits. So we've got 200 bits available of memory. If sometime later we transmit more data, then again that's stored in memory. The second frame is stored in memory. Another 100 bits. So of our 300 bits, we're currently using 200 bits. Another piece of data is transmitted, received. So this is at the receiver. The memory is now full at the receiver. we're storing in this piece of memory 300 bits of data. We make space available when the network layer at the receiver is ready to take that data out. And that depends on the speed of the computer and what the application and the protocols are doing. We cannot predict exactly when that will happen. In particular, if the speed of the receiver is quite slow at processing this data, then it may happen that we've got the memory full at the receiver. We're currently storing 3 frames or 300 bits. The maximum size is 300 bits. What happens if we transmit more data? We transmit frame 4. What happens at the receiver? Overflow. What does that mean though? Where does this 100 bits that we receive go? Overflow, I think, points to the problem. Either that 100 bits of frame 4 that we receive is thrown away. We cannot save it in memory because we have no memory left. So either we throw away this frame, we ignore it, or throw away one of the existing ones. In either case, we're going to lose 100 bits of data. That is, the transmitter has transmitted 4 frames, a total of 400 bits, but we can only store 300 bits at a time. If we transmit 4 while this is full, one of those frames is going to be discarded or lost. We're going to lose the data. It's not going to be received. That's a problem. And we want to avoid that problem. And this is the problem that flow control protocols try to fix, because we get an overflow of memory at the receiver. What we want to do to avoid this is to make sure that the sender doesn't send such that we overflow the receiver. In other words, slow down the speed at which the sender sends. If it sends too fast, the memory may overflow. Therefore, get it to slow down so that the memory does not overflow. And that's what we get flow control. When is some space made available in our receive buffer or receive memory? Well, as we process the data, as we receive it and send it to the network layer, if we've delivered it to the network layer, then it's removed from the memory. So as we receive frames, we put it into memory. As we deliver the data to the network layer, we take it out of memory. So if we've just delivered frame 1 to the network layer, then we can receive another 100 bits because we're only storing 200 bits. So the dynamics change depending on the speed at which we deliver to the network layer. So we need a flow control protocol such that the transmitter will not send too fast such that the receiver is overflowed. And that's what we're going to look at most of today. Flow control aims to ensure that the sender does not overwhelm or overflow the receiver. Because the buffer, that is the portion of memory allocated to receive the data, may overflow if we send too fast. When may this happen? This may especially happen if you have 2 computers and the transmitter is much faster at processing and sending than the receiver. So we're sending quite fast. As we receive, it's very slow in processing each frame, and therefore it could be overflowed. The result or the problem of such an overflow is that data is lost. If we have 3 frames in memory, we receive a 4th, we're going to lose 100 bits. We cannot do anything with it. Losing data is not good. We'll have to do something like retransmit, which will reduce our performance. So flow control tries to prevent the buffer overflow. And when we look at the flow control mechanisms in the next few slides, we'll assume that there are no errors. That is, everything that we transmit is received. But there may be delays, propagation delay, transmission delay, that go up and down over time. We'll see the impact of that. We're looking at the data link layer. Flow control is part of the data link layer, but towards the end of this course we'll also see it's part of the transport layer. TCP, which you use every day, includes flow control. So in fact the general mechanism is quite important. Now, before we look at how flow control works, we need to describe something else. We need to describe how we're going to illustrate the operation of protocols. So this is something different, but it's going to help us in explaining how protocols work. You know these 5 layers of the stack. There were several questions in the exam about what each layer does, but you've memorized the 5 layers. We're dealing with the data link layer. But in general, what happens, we have data, the application layer processes it, sends it down to the next layer, and so on, until it's transmitted across our link, and then it's received, and that data is passed up through the layers to the person or the receiver at computer B. At each layer, there may be processing delay. That is, what happens within the application layer happens on your computer. It takes some time. It may be very, very small, but there's some processing delay at each layer. There may be some queuing delay. We saw in the previous 2 slides ago that we have some memory. Frames go into memory. They have to wait in that memory for some time. That's queuing delay. They have to queue up before they're transmitted. Over the link, we have transmission delay. The size of the data that we want to send divided by the data rate. And we also have propagation delay, the time it takes for a bit or a signal representing a bit to propagate across that link. So they're the components of delay. Processing and queuing in each of the layers, and transmission and propagation across the link. So this is not about flow control. This is generally about how we can analyze and illustrate protocols so that we can explain them. If we focus on the data link layer, for an example, we can think of the general steps as, at the start, data arrives from the higher layer, the network layer. It may be queued, that data may have to wait in memory, therefore incur some queuing delay. It is processed, so there may be some processing delay. And then that data is transmitted as a frame, and that incurs some transmission delay. It propagates across the link, and at the receiver, it's processed. Some delay is incurred. It may wait in a queue in memory, and then is sent up to the network layer. That's the normal set of steps for the flow of data through the data link layer. What we need is some nice way to illustrate what happens and illustrate the timing of those activities. And this is one way to do it. We'll show it here and then maybe one on the board. So this is what's called a time sequence diagram or a message sequence diagram. It's a diagram that illustrates the transmission of frames or of packets between 2 nodes and illustrates as a function of time. A and B are the 2 devices, the transmitter and the receiving device. As we move down in this diagram, time increases. So we say this is the start, and then as time increases, different things happen in this diagram. And the diagram tries to illustrate what's happening. Let's say at this point in time, data arrives from the network layer. Someone has pressed send on their computer. That triggers data to come from the application to transport down to the network, and eventually it arrives from the network layer at the data link layer at this point in time. If there's no processing or queuing delay, we may start to transmit that data. And we transmit it bit by bit. If we have 100 bits to send, we take the sequence of bits, map it into a signal, and transmit those signals across the link. So we can think of it as we transmit the first bit, and then the second bit, and then the 100th bit, is the last bit transmitted. And the time it takes to transmit is simply the data size, the number of bits, divided by the data rate. This diagram illustrates as this rectangle, this box here, the transmission occurring. That is, at this point in time, we start to transmit our frame, our sequence of bits. And at this point in time, we've finished transmitting that frame. So that's a common way to illustrate that, okay, the transmission takes some time. Remember, time is increasing as we go down. As we transmit a signal, it takes time to propagate across the link. So if we transmit the first bit, or the signal representing the first bit at this point in time, it takes some time to get to the receiver. And we illustrate that by, okay, if we start at this time, then it arrives at this time, sometime later. So we can think from the receiver B's perspective, it has received the first bit of the frame at this point in time. So this is the propagation time between here and here is the propagation time. And we transmit the second bit. The second bit will be received slightly after. And the third bit, the fourth bit, and so on. And then the 100th, or the last bit of the frame, is received. That is, the last bit was transmitted. It took time to propagate across the link, and therefore it's received at this time. So B, the receiver, has received the entire frame at this point in time. And then there may be some processing. In this example, there's no illustration of processing. Eventually, the data that was inside that frame is delivered to the network layer. So we're going to use these types of diagrams to illustrate how protocols work. So that was trying to introduce the basic concepts. You'll see many examples of them today and the next few lectures. And by using these diagrams, it's easier to see how the protocol operates, and also to see the timing involved in the different activities. The delay to transmit this, or to deliver the data from A to B, if we start at this time, then the data is delivered at this time. So if we can calculate, we can visualize the delay starting from here, finishing here. And in some examples, we'll put numbers to that. Or a little bit simpler, we can think as this is the transmission time, and this time is the propagation time. We could also add in processing and queuing time if we needed. Let's try and use these concepts to explain how flow control works. The most basic flow control protocol is called stop and wait flow control. It's very simple. Remember, flow control is the sender cannot send too fast such that it overflows the receiver. That is, control the speed at which the sender sends so that it doesn't overflow the receiver. The basic way to do that is to allow the sender to send one frame at a time, one block of data. Send one frame. When that's received, the receiver sends back a special frame, an acknowledgement saying, "Thank you, I've received that. You can now send me a second frame." And it continues like that. And from the sender's perspective, we transmit our data, we stop and wait for an acknowledgement, and then we can transmit more data, and then we stop and wait for another acknowledgement, and so on. And hence we get stop and wait flow control. So in this protocol there are two types of frames. One frame that contains data, let's just call it the data frame, that contains the information we want to get from the sender to receiver, and a second type of frame called an acknowledgement frame, or an ACK frame, and that acknowledges the receipt of data. And remember, a protocol follows a set of rules. The rules here: the source can transmit a data frame. When the source has transmitted a data frame, it must wait for an ACK frame. It cannot send a second data frame before it receives that ACK frame. So a source waits for an ACK frame before sending the next data frame. From the destination's perspective, when the destination receives a data frame, it can reply with an ACK frame if it's ready for more data. If it's not ready, it doesn't have to reply. And if the destination, the memory at the destination is full, which means it's not prepared to receive any more, otherwise there'd be an overflow, then it does not send an ACK back until the memory has some space for more data. So in the example that we had, the receiver could receive a total of 300 bits, or 3 frames, if we say our frames are 100 bits. So it could receive 3 frames. If we have 3 frames in the memory, then after receiving the 3rd frame, the receiver will not send back an acknowledgement. And because an ACK doesn't come back, the transmitter will not send another data frame. It's not allowed to if it follows this protocol. So quite simple protocol to provide flow control. This is an illustration of that, just one example. Node A sending data to node B. The data from the network layer arrives at different times. That is, some data, let's say data 1 arrives at this point in time. Some time later, some random time later, some more data arrives from the network layer to be sent to B. And then some more data down here. At the start, data arrives. So A transmits that data in a frame, say frame 1. Takes some time to transmit. Takes some time to propagate across the link. The entire frame has been received by B at this point in time. Although the diagram doesn't show it, note that also the first bit of that frame would be received around here. The second bit, the third bit, and the last bit received here. We cannot do anything with that frame until we've received all bits of that frame. So from the delay perspective, or the operation, we care about when is the entire frame received. Okay, it's received here. In this example, let's say the buffer is full when we receive that frame. So we've received frame 1. At B, the buffer or the memory is full. We have no more space available. Therefore, we do not send back an acknowledgement just yet. If we don't receive an acknowledgement, we cannot send any more data. Just ignore this. From A's perspective, we transmitted a frame, and then we stop and wait for an acknowledgement. We're waiting, we're waiting, we're waiting. We haven't received an acknowledgement. There's some more data to send. We're not allowed to send it. According to the rules of the protocol, we cannot send this second data frame until we receive an acknowledgement for the first. So even though we have data to send, we must wait for an ACK. When does the ACK come? In this example, B received the data. There was no more space available in the buffer, in memory. But then at some point, the data 1 was delivered to the higher layer, which means there was now space in the memory available. So because there's data removed from the memory at B, there's more space available for another frame to be received. So it sends back an ACK saying really two things. Thank you, I've received data frame 1, and I'm now ready to receive the next data frame. That's the one way we can interpret the ACK here. Send back an acknowledgement. It takes time to transmit. It takes time to propagate. And the entire ACK is received at this point in time. And now, because we have data ready to send, and because we've received the ACK for the previous frame, we're allowed to send the next data frame. We transmit that. It's received in its entirety here. In this example, the data in frame 2 is immediately delivered to the network layer, and therefore we immediately send back an ACK. It arrives here. A does nothing at this point in time because it has no more data to send. We had data 1 transmitted and ACK, data 2 transmitted and ACK. At this point in time, there's no more data to send. We do nothing. And then data 3, some more data arrives, so we transmit, and we could follow that diagram as more data comes. So the source transmits, stops, and waits for an ACK to come back. The destination, when it has space available in the buffer for the next frame, transmits the ACK, acknowledging the data of the previous frame. Very simple protocol, but achieves the objective of not allowing the transmitter to overflow the buffer or the memory at the receiver. The receiver controls the speed at which the sender sends. Here you go. In practice for your final exam, here's your first task for today. Answer this question. Similar to what we just covered, but now we have some numbers involved. And I know you're all very fast at calculating transmission and propagation time, so it'll be easy. A source, say computer A, has 3 frames to send. 3 blocks of data. Each block is 1,000 bytes in length. There's some processing time at the destination. Each data frame contains 1,000 bytes of data plus a header. So it's going to take some transmission time. There's an ACK frame which has some size. We know the distance of the link. We know the speed of the link. Therefore, you can easily find the propagation time. We know the data rate of the link. You can find the transmission delay of the data frame and the ACK frame. What is the throughput? All right, the first step that you need to do now is to try and draw a diagram like the previous slide that illustrates what happens with a stop and wait protocol in this case. So draw a diagram similar to this, which fits this scenario. Your diagram does not have to be to scale, but it should illustrate the transmission, propagation times, and eventually you'll calculate the values of those times. It helps to have a piece of paper, probably an A4 sheet, as opposed to a very small piece of paper. If someone's got some blank paper, some people could use it. There's blank sheets at the end of your handouts. once you have the diagram that illustrates the flow of frames, then you can start calculating the times it takes to do each step. So the source, A, at the start, has 3,000 bytes to send, or 3 messages, 3 separate pieces of data, each of 1,000 bytes in length. So let's say data 1, data 2, and data 3, each are the same size. This is what comes from the network layer to the data link layer at A, at the source. What does the source do? Let's say instantaneously it receives 3 messages, each of 1,000 bytes. What does it do? Does it send all of it to the other side? What's it do? You've got a diagram there, it looks okay. After we receive the 3 blocks of data from the network layer, what does the source do? Yeah, at the start. So at the start, let's say immediately we have 3 blocks of 1,000 bytes. What does A do, or the source?
Send data 1 to B and wait for acknowledgement.
Send data 1 to B and wait for an acknowledgement. Good. Now we assume at the start that this is the start of the protocol. We don't have to wait for a previous acknowledgement. That at the start we're immediately allowed to send. How much can we send? We have 3,000 bytes of data to get from A to B. That's our goal. How much of that do we send at the start? How much? 1,000 bytes, correct? 1,000 bytes of data because of this part of the question. If we had, it's just so in this example the numbers are the same, 1,000 and 1,000, they don't have to be. If this was 500 bytes here, it means a data frame contains 500 bytes of data, then we can only send 500 bytes in the first frame. So each data frame is distinct or separate from the data that arrives from the higher layer. So we've got 3,000 bytes of data to send. We are allowed to send 1 data frame at the start, and that data frame is going to contain 1,000 bytes of data plus a 20-byte header. To illustrate the transmission of this frame, I'll draw it like this and call it frame 1. When I say frame, I mean a data frame in this case. Data frame 1. This, in the diagram, illustrates the transmission of the data frame. And one way to help in calculating the throughput, we're going to need the total delay. One way to help in calculating is think, okay, when we start, that is time 0. this point in time, time equals 0. 0 seconds. That is the start of what's happening here. And as we go through, determine what is the time when we've finished transmitting and what is the time when other events happen. We're going to use that data to solve what is the throughput. We start transmitting the first data frame at time 0. When do we finish transmitting that data frame? Try and calculate that. What is the time here? If we start transmitting at time 0, if we have a clock and it takes time to transmit, when do we finish transmitting that frame? How are you going to calculate it? Transmission time? Total size. Data size divided by data rate. So this data frame, let's draw it over here. Each data frame, they're all the same in this case, each data frame contains 1,000 bytes of header plus 1,000 bytes of data plus 20 bytes of header. If I wanted to draw it, there's the data and some header, HDR. In our example, there are 1,000 bytes of data, 20 bytes of header, giving us a total of 1,020 bytes to transmit. So the data frame is 1,020 bytes in length. Transmission time of the data frame equals the data size divided by the data rate. 1,020 bytes divided by, in our question, the link data rate is 1 megabit per second, which means we can transmit 1 million bits every second. We've got 1,020 bytes to transmit. You can use your calculator to solve that. It's 1,020 times 8 to convert to bits, which is 8,160. Divided by 1 million bits per second gives us microseconds. It's a U or mu, not milli, microseconds. The transmission time of data frame 1 is 8,160 microseconds. That's using normal concepts we've learnt at the start of the course. Therefore, if we start transmitting at time 0, we'll finish transmitting at time, or 8,160 microseconds afterwards. And instead of writing the units here, let's assume all these blue numbers are measured in microseconds, just to make it easier to read. If I start my clock, time 0, it will be at 8160 microseconds when we've finished transmitting. Keep going with the next steps. What happens next? This is what we have on the board over here is our normal formula for transmission delay. I have a frame of some size. How long does it take to transmit out of my computer? Transmission delay, or the transmission time of that frame, is simply the size of the frame divided by the speed at which I transmit the frame. Data size divided by data rate. Data size was 1020 bytes. Our data rate in the question is 1 megabit per second. So the transmission delay, and also when you calculate propagation delay, it's nothing different from what you've done before. We'll just use that to work out what's the total time to perform all these operations. What happens next? After A has transmitted that frame, what does the source A do? Right. So at time 8160, computer A is finished transmitting. What does it do now? What does A do? A has, think just from computer A's perspective, A starts transmitting, it's transmitting, finished transmitting. What does it do now? This transmission is sending to B. So the diagram just illustrates the time it takes to send that frame to B. Remember, when we have a bit to transmit, we may convert that into some signal. So if this was the first bit here, bit 1, then since we can transmit 1 million bits per second, it will take 1 microsecond to transmit a bit. We'll transmit the first bit, and then 1 microsecond later the second bit, and then the third bit, and so on. When we transmit the first bit, it comes out of our computer as some signal. And that signal propagates across the link. When we transmit the second bit, it comes out of we're taking the bit and transmitting a signal out of the computer. And that second bit propagates across the link. And then the third bit and the fourth bit and all of the bits, think of we're transmitting them one at a time. Each bit has to propagate, or the signal representing each bit needs to propagate across the link. So the signal representing bit 1 is received by B at this point in time, which is what time? At what time does B receive the first bit? Try and calculate that. When is the first bit received by B? The first bit is transmitted at time 0. It propagates across the link, and therefore it's received at some time later, which is what? When is it received? You've got the right equation. I'm not sure if you've got the right number. It's received, we need to know the propagation time. That is, transmit at time 0. That signal that comes out of the computer takes time to propagate across the link. The propagation time, we'll calculate over here. Again, using the knowledge from before the midterm, propagation is the distance, 2 kilometres, or 2,000 metres, divided by the velocity of our signal. And to make this example easier, 2 by 10 to the 8 metres per second is the speed or velocity of the signal. Distance divided by speed. which is 1 by 10 to the minus 5 seconds, which is 10 microseconds. So the propagation time of a signal across our link is 10 microseconds. So if the signal is transmitted at time 0, it takes 10 microseconds to get to the other side of the link, and therefore is going to be received at time 10 at B. The first bit, that is. The second bit is transmitted slightly after, a short time after, and it's going to take another 10 to propagate. I'm not going to draw all of the bits, but we have 8,160 bits. The last bit was transmitted at time 8160. It propagates, and it's received at what time? When is the last bit received? When's the last bit received? 8,170. Good. So remember, computer A is transmitting the bits one at a time, or transmitting the signal representing each bit. And once it's transmitted the first bit, it moves on to the next bit, and so on, until we transmit the last bit, and then computer A is finished transmitting. But the signal takes time to get to the other side. In our case, it takes 10 microseconds to get to the other side. So if we start transmitting at 8160 for the last bit, it will receive at time 8170. In other words, the entire frame is received at this time. So between time 10 and 8170, B is receiving the frame, bit by bit. And between 0 and 8160, A is transmitting that frame. We've lost some. Of course, I would draw all the bits, but we don't have space, so I'll just hide this, just so we can read our diagram. So, all right, we can show the first bit. So we transmit the frame, and it's received at this time. What happens now? Let's focus on computer A. After transmitting, what does computer A do? Again, what does computer A do after transmitting that frame? What is the name of the protocol we're talking about? Simple question. What's the name of the protocol we're talking about? Some type of flow control protocol. What's its name? No. What's the name of the protocol? Stop and wait. Computer A transmits the frame. When it's transmitted, it stops and waits for an acknowledgement. So it does nothing. Computer A doesn't transmit anything, it waits for an acknowledgement. So we can say we're waiting. So let's look what computer B does then. Computer B receives the frame, and in our question it takes 1 microsecond to process the frame. So then we process. If we start processing at 8170, we'll finish at 8171. With a processing delay of 1 microsecond, we've finished processing at 8171. Let's say here. Now this diagram's not to scale, just I've spread it out so that we can at least see the different events. Definitely not to scale. After we've processed the frame, the question doesn't give us any more details, so let's assume that we've got enough space in memory, so we'll send back an acknowledgement frame. If B has space available in memory to receive more data, it will transmit an ACK. It sends a frame back to computer A. And that frame is called an acknowledgement frame or an ACK frame. The ACK frame has some size, 20 bytes in our example. So the transmission delay of the ACK frame, we calculate it the same way as the data frame. We have 20 bytes to transmit. The link speed in both directions is the same, 1 megabit per second. Which is 160 microseconds. 20 times 8 divided by 1 million. So the time to transmit the ACK back takes 160 microseconds. We receive the data at 8170, 1 microsecond to process, start transmitting the ACK, and therefore we'll finish transmitting the ACK 160 microseconds later. 8171 plus 160 . This is 8171, 8331 here. And the same as with the data frame. We're actually transmitting bit by bit. Transmit the first bit, it propagates and is received. The second bit, the third bit, and the last bit, and is received. The propagation delay again depends upon the distance and the velocity, which is the same in both directions. The distance is the same no matter which direction we're transmitting, and the speed at which we transmit. So the propagation delay is another 10 microseconds. Start transmitting at 8171. The first bit takes 10 microseconds to arrive at A. So the first bit would arrive at 8181. We transmit the last bit at time 8331. Therefore, the last bit arrives at 8341. We've received the entire ACK frame at time 8341. Data transmitted, some processing, ACK is transmitted. After transmitting the ACK, B does nothing. In this case, all that B does is receives data, process, send an ACK, and then do nothing. Computer A transmitted the first data frame, which contained 1,000 bytes of data. It stops and waits. It's waiting for an ACK, starts to receive the ACK, has fully received the ACK at time 8341. 8341, it can start transmitting the next frame. With stop and wait, we transmit one data frame, receive an ACK, we're allowed to send the next frame. Then we wait for an ACK. And it goes like that until we run out of data to send. So I'm going to move my diagram, but at this time we've received the ACK. Assuming there's no processing time, we've sent one block of data. We're now allowed to send a second block of data in the second frame. So we have a transmission of data frame 2. And I'll continue over here. So continuing just after we receive the ACK at 8341, immediately transmit the data frame. And follow the same procedure. How long does it take to transmit the data frame? Well, it's the same size as data frame 1, so it takes the same transmission delay. 8160 microseconds. So we start transmitting at 8341 plus another 8160. Finish transmitting. What do we get? 16501. 8341 plus 8160. That propagates to the other side. The first bit arrives, the second bit, and finally the last bit arrives. And because the propagation delay doesn't change, we transmitted the last bit at 16501. We receive the last bit with a 10 microsecond propagation delay of 16511. Processed for 1 microsecond. There's a processing delay. Transmit the ACK back. Processing adds 1 microsecond. Transmitting the ACK adds another, so that's 16512, adds another 160 microseconds. The ACK is the same size as the first ACK, therefore it takes the same time to transmit. 16512, what is it? 16672. That propagates back to the other side. Although the first bit propagates, we usually do not draw that because what we care about is when does the entire frame arrive? When does the last bit get here? So I haven't drawn the first bit and all the other bits because I care about when the last bit arrives. Plus 10 to propagate. The second data frame has been delivered and acknowledged by the time 16682 microseconds. And we've got another frame. And it does exactly the same. Transmit the data frame, process, transmit the ACK. We will not go through all the steps. We will not calculate. Transmit, process, send the ACK. And it's going to arrive when? At time 25023. Let me check if I've done it correct. 25023. You can do it in your own time. It's just here plus 8160 plus 10 plus 1 plus 160 plus another 10. Or simply you see this time 0 to 8341, everything is identical to this time. Same data size, same propagation, same processing. So the time from here to here is in fact 8341 microseconds. The time from when we start from a data frame until we receive the ACK, in this example, is always 8341 microseconds. Because the data frames are the same size, the propagation delay is the same, and processing is the same. And in fact, the question says if we have three pieces of data to send, but if we had 1,000 pieces of data to send, we could do the same thing. You just repeat this another 997 times. Each frame to be transmitted and receive the ACK takes 8341 microseconds, and we repeat and repeat and repeat. So it leads us to the last part of the question, or the answer we're looking for is, what is the throughput in this case? Try and calculate the throughput. Yep.
If there is 3 frame, right, the last frame will not send ACK back.
No. Sorry. So this was the first data frame, process, ACK. The second one, the same. Data frame, propagate, process, ACK. Third frame, the same. Data frame, I just haven't drawn it in details. Data frame, process, here's the ACK here, comes back. So each frame in this example, we've got those same steps happening. This is data frame 3, and this is the ACK. And if we had more frames, the same would happen. That's the example in the slides. Let's go back. What we just did on the board is not this one. Looks the same, but there's some subtle differences. It's just a different example. This one I haven't finished. That is, in this one, in this slide, yes, we'd have propagation ACK, and there may be more frames. Could go forever. Or let's say we had 1 gigabyte to send. Send 100 bytes, the next 100 bytes, and do that until the entire 1 gigabyte is transferred. So yes, that previous slide we didn't finish the diagram. This one we have finished the diagram. Yep.
Does it mean that we're not going to do that?
So one of our rules, which we haven't encountered in this example, in our example we've assumed that the receiver always has memory ready to send. So it's always got space to allow another data frame. But if we don't have space, then we can stop the flow by not sending an ACK. Let's see if we can illustrate that. No, we'll illustrate that after you find the solution to this. This is just one example. It doesn't consider all cases. First, what is the throughput for this example? Who has an answer? What is the throughput? Then we'll look at some other cases. Anyone have a number? First, let's give you let you recollect what we mean by throughput. Throughput is the rate at which we receive real data. The rate, so the speed at which the real data is received. So think about how fast is B receiving the real data? How many bytes per second or bits per second? For the first frame, from B's perspective, at time 10, we started to receive some data. And let's see what we can do. So at time 10, B started to receive data. And if we have, well, maybe we need to draw some more to cover this. How much real data per frame? That's the first part we need to know. 1,000 bytes of real data. I say real data to distinguish from this is a data frame. This is a frame that contains the data plus a header. The header is not user data. It's additional overhead. The data that we want to count for throughput is this 1,000 bytes. So every frame we send, we're sending 1,000 bytes of real data. What's the rate at which it's received? Well, if we see the pattern, for every frame that we need to send, we start and we finish after the ACK is received. And in the next frame, we transmit and we receive, or we can transmit the next frame after the ACK is received. And then it's the same. And if we had more data to send, it would be the same again. That is, we have 1,000 bytes of real data. And for each frame, the time it takes to get that delivered to the other side, a total time of, this diagram gives it easier, start at 0, finish at 8341. And then we can send the next frame. And the next frame, start at 8341, finish at 16682. What's the difference? The difference between these two numbers is simply 8341. The next frame, start at 16682, finish at 2503. The difference, if I can draw straight, is 8341. Each frame to transmit, get the ACK back, takes 8,341 microseconds. So on average, we're transmitting 1,000 bytes of real data every 8,341 microseconds. And because everything's being received, we're receiving 1,000 bytes of real data every 8341 microseconds. And you need a calculator to answer that. And the answer (959,117 bits per second). Our data rate of our link was 1 million bits per second. We're receiving at a rate of 959,117 bits per second. Just 8,000 divided by 8341 microseconds, or 95.9% efficiency. That is, this number divided by 1 million bits per second is 95.9%. And you can, if we're 95.9% efficient, it means in this case we're spending 95.9% of the time transmitting real data across our link. So now you see calculating throughput is more complex than what you've done up until the midterm. In this case, during this period of time, we're not transmitting anything. That's an overhead. And that reduces our throughput. Make sure you can calculate this. You see, all it is the real data divided by the total time to deliver that and get the ACK. And the efficiency is simply the throughput divided by the data rate, expressed as a percentage. When you can calculate that, you should be able to answer how do you increase the efficiency, or what factors impact upon efficiency. We'll finish that for today. Tomorrow morning we'll finish this example. We'll cover some other aspects of stop and wait flow control, and towards the end of the lecture I'll let you look at the exams. So make sure you've had a look at the solutions so that you can have a quick look at the exams tomorrow and see where you went wrong. Let's continue tomorrow.